Thanks everybody for coming. I'm just going to give a little introduction and getting started here as we get started. We have a number of instructors and volunteers, so I'm sure people will need help, and we're happy to give help. Over here we have Luis, maybe raise your hand, and Eric is helping us out, and then Anna, and Jean-Christophe, JC, and Steve, and Ashish. Raise your hand. So we're all happy to help you out. And so what we want to do for this exercise is going to be a lot of hands-on work and working with each other, and it's going to be a lot of fun. So you're going to work with a partner. So luckily, the person next to you is one of the best researchers that you've ever met. So introduce yourself to the person next to you, and that'll be your partner. Very good. And very good. So we have these preparation tasks, and if you worked on that, that's good. If you had issues, then it's good because you're in good company, but we'll help you work through them. So if you had issues, please raise your hand, and we'll come get you. And then also, throughout the tutorial, we can help each other work on this Mozilla Mopad, Etherpad. And if you open that up and keep track of that, that's where that is. And the document will be based it off is this. Here's the URL of the rendered website. And this is our agenda, and we'll be working from there. Okay, so that's kind of your home page. And then we'll go from there to a number of different sessions covering different topics. So you want to keep that close hand in your browser. Okay, so I'll go around and distribute some more fun material, and if you have questions, make sure to ask them. And for now, I'll hand it off to Dr. Lee Ibanez, who's going to talk a little bit more about briefly our motivation and history of reproducible research.
So good morning, welcome. So this should be a lot of fun. What we are going to do today is to essentially demonstrate that all the tools that you need to do reproducible research are at your hand. They are already out there, and thanks to many of you in the room, actually. So this is an exercise on using those tools to exercise the process of doing reproducible research end to end. So that's the art that we want to go, from data acquisition up to publication. And make sure that whatever you are publishing in an article, somebody else can replicate it. And it's not just a possibility, it should be something that we exercise on a regular basis. So what do we care about this? Why are we so concerned about the reproducibility in scientific research? And the problem starts with this credibility crisis. So we have grown accustomed to the notion that when you publish an article and it appears in some reputable journal, this is something that you can trust. It's information that you can build upon to go to the next step. But unfortunately, what happens, if any of you have been involved in the peer review process in modern publications, you know that the reviewers do not replicate the work. The reviewer reads the article and makes sure that it kind of makes sense, that it's not too wrong, that it's not too crazy. Make sure that he is in the citations. And then you move forward to the publication process. However, I mean, this makes sense for researchers and their careers. But there are organizations out there, and there is people out there who are in the receiving end of the publishing system, and for whom the actual content of the papers do matter, whether this actually works or not. And one of those are the pharmaceutical industry. So you go to the biologists, and they publish the papers. They get their job promotions, tenures, applications, and so on. But the people on the receiving end, the final end, will be the patients that are supposed to receive treatments through medical procedures, medical devices, or drug development. So for pharmaceuticals, really care whether the content of a biology paper does work. So this is an interesting anecdote or an exercise that people did at a pharmaceutical company called Amgen. And they essentially look at a collection of articles, key papers on cancer research, and they attempted to replicate them. And they found that 90% of these articles could not be replicated. Now, these are not the papers that I write or the papers that my friends write. These are papers that are kind of Nobel Prize level articles. And they turn out not to be reproducible. So essentially, the framework of knowledge that we have about what we think we know about cancer research, 90% of it is not substantiated. And the failure to get that verification is part of how we have been implementing the publication system and the peer review system. So what these people did, they took 53 articles on cancer research, landmark studies, so not the secondary papers. These are really the key articles that essentially build the dogmas that we have about what cancer is. And only 6 of those articles could be replicated. Now, this is also a top kind of team, and they were working in collaboration with the people who published these articles. So it was kind of as close to you can get to ideal conditions today. So it was collaborating with the authors, having access to the materials, having the facilities to do it. And despite of that, 90% of those articles could not be replicated. So as a secondary effect, or as a cascade effect of that exercise, there's this organization called the Science Exchange that is a great idea. It's a market for scientific research. So if you are doing your research and suddenly you need a task to be executed, you can go to the Science Exchange with your credit card and order a lab test or get time in a particular type of machine, in a microscope. You can get to the Science Exchange with your credit card, order an experiment in the space station. So that's how populated it is. If you have yourself facilities that you have extra time on, and you want to essentially put them in the market, you could offer them in the Science Exchange and be paid by somebody using those facilities during the time that you are not using them. So one of the things they did is that they pursued this cancer reproducibility exercise. So they are going to repeat this study. And they got a $1.3 million grant to do this exercise. So they target 50 papers. And they are going to use this grant in order to replicate those papers. Now, you guys are smarter than me, so you have already calculated that this is about $30,000 per article. So this is how much it costs, or we believe today. This is as close as we get today to know how much it costs to replicate somebody else's work. Now, of course, your mileage varies depending on the kind of experiment that you're going to replicate. Now, how much it costs one paper, the estimation is about $500,000. So if you look at NIH, for example, the annual budget of NIH is $30 billion, and the output of NIH is 65,000 papers a year. And you divide those numbers, and you get that about $300,000 to $500,000 is what one paper costs. This is the total cost of producing the paper, end-to-end, salaries and equipment and university administration and so on. Now, in this exercise, they also run into some interesting result, and is that when you go to websites and order antibody reagents that are supposed to be detecting particular pieces of proteins or particular pieces of DNA, it turns out that they don't work as expected. So they have to embark also in an exercise of ordering many of these reagents and testing them. So essentially doing the consumer report of biology compounds. That again shows how much we need to look back at the basics and verify whether the materials that you're using when you're doing scientific research actually perform as expected. So this all brings us back to the principles, and this is the motto of the Royal Society, which is believed to be one of the first scientific societies. And they actually started not in a university. They started as a subversive movement against what universities were at the time. So this is the 1600s, and universities were the places where people studied natural philosophy. So it's essentially people sit and think about the world and think, would it be nice if the orbits of planets were circular? That would be really cool. And then they develop a theory along those lines. As long as it's self-consistent, that's what natural philosophy was at the time. Now, this group was reacting against this conception of how we gather knowledge about the universe, and they thought that that thinking was really cool, but it was better to know what really things were, and that only experiments could bring you there. So they essentially took on this motto, which means take nobody's word for it. So the fact that somebody describes to you an experiment and tells you what the results were, that is nice, it's informative, but it's useless until somebody else goes through the same process. Not only once, but multiple times. And how many times is necessary? There is no particular number at the end. So every replication just builds confidence on the fact that this may actually be happening. So there is not a particular limit to how many replications you should make. And this is something that is interesting to remember about these early scientific societies. They were not the kind of scientific conference that we have these days where people go in the podium and show a paper and then the next one passes and we circulate through that process. These people were getting together to replicate experiments. So the scientific societies, the real scientific societies of the early days, were places where somebody will find some interesting observation. They will write a letter to the society, and the fellows of the society will get together on a Saturday in the garage equivalent of the 1600s and will attempt to replicate the experiment. And if they succeeded, they're going to disseminate it further. So if you remember Robert Hooke, the guy with the Springs law, his job as the Royal Society was to be curator of experiments. So his job was to make sure that the experiments could be replicated. That was part of what he did. Now, it's not just biology. If you saw the earlier clip, similar thing happens in economics. And so this is the Rogoff and Reinhardt article. This is a very key article. These are two Harvard economists. It doesn't get any more serious than that. They brought this paper describing how the ratio of debt to GDP in a country could prevent growth, economic growth, essentially. And this paper has been used to drive economic policy, not only in the US, but also in Europe. And it turns out that the paper has a couple of small mistakes. They use an Excel spreadsheet in order to do some computations. And in the process of doing those computations, they excluded some small, not very important countries like Japan and Canada and Australia. And after removing those, accidentally or on purpose, it's hard to know what happened there, they got to a certain conclusion, essentially saying that if you have a certain ratio of debt, you are in trouble in order to do economic growth. And therefore, you have to start tightening your belt and making savings, and then the economy will get better. Now, it turns out that Thomas Herndon, this is a graduate student, he was in a class, and the professor of this class thought that it was a good idea that to teach the scientific method to the students, they should go and learn from the best, these guys. So they grab papers from reputable researchers, and they attempt to replicate those papers in order to learn about the methods. And what happened to Thomas is that he was not able to replicate these results because using public data, he was not able to replicate them. So he contacted authors, got access to the Excel spreadsheet, and after opening and inspecting it, he realized what the problem was. Now, what's curious here is that this is a very rare occurrence. So this is what peer review should have been all along, but this is not how we exercise that process. You already saw the clip. So the point to be made here is that it's all across the board. Because the process that we have for reporting the results of research today are based on a paper that is outdated technology. So what we're going to do today is essentially go back to the basics of the scientific method. And one of the most important things to remember here is that the key to the scientific method is reproducibility. We have been confused on thinking that it's novelty. You go to conferences and journals, and they ask you for new stuff that has not been published. This shows you how much the publishers are dominating the activity of the scientific research field. Novelty is irrelevant in science. There is no point in having something that is new because the scientific research field is not the patent office. That's a different type of environment. What matters in research, in scientific research, is whether the thing that you found is real. So whether it can be replicated, because that's the only sign, is the only way to make sure that whatever you reported is actually real. So there is this distinction to be made. There is the profession of being a researcher, that you're pursuing knowledge, and there's the profession of being an inventor. Inventors are in the business of finding new stuff and going to the patent office and then going into business. That's one type of profession. Researchers are different. They are gathering knowledge, and for them, reproducibility is the key signature of their profession. All right, so what we're going to do today is, this summarizes everything. So if you're a true scientist, you do this, you replicate. And what we're going to do today is to go from the process of acquiring data, sharing data in a public environment, process this data, publish a paper with this data, and then switch and replicate that paper. That should be our closing at the end. Now we're going to start inspired by this man, Anthony Leeuwenhoek. He was not a university professor. He was actually a seller of drapes. And because in his profession it was very important to know about the quality of fabrics. So he used lenses. He used magnifying glasses in order to verify the quality of this fabric. And he became very, very good at using these magnifying glasses. So he also became interested in microscopy, and he was the first person to observe bacteria. So Anthony Leeuwenhoek, in 1665, wrote a letter to the Royal Society describing that he has been able to see thousands of living organisms in a drop of rainwater. Now, if you can imagine this at the time, this is equivalent to me coming to you and saying that I found 100 aliens living inside of this laser pointer. So there should be some space for disbelief and wanting to have proof. So at the time, because of the Royal Society were receiving this letter, it was up to Robert Hooke to replicate this experiment. So that's the process that we're going to go through today. All right. Any questions, observations?
If anybody needs help, just put your hand up and one of us will come around to you.
Okay, thank you.
All right, so thank you, Luis. And now we're going to go on to...
If you're on OS 10 and you are having trouble getting Docker, please check out the boot to Docker, and there's some instructions on the move pad, so please check those out. And again, raise your hand, get our attention, we'll come around and help. Thanks.
Thank you. So since Leeuwenhoek did such a great job, we're going to follow in his footsteps and try to reproduce his work. That's our exercise for today. So we're going to, in some sense at least, work through the workflow of going from nothing at all to collecting data, sharing this data with our peers in the scientific community, and doing some computational analysis on this data, and processing it, editing our code and version controlling our code with Git, doing regression testing, creating a publication, and then putting that publication out there. So the first step is just really a fun step of kind of reproducing the data collection of Leeuwenhoek. So if you go to the page here in our documents directory, there's an image acquisition step. So if you go there, so what we're going to be doing is creating our own microscopes and collecting some of our own images on our cell phones or tablets. And this will be a fun experiment. If you have difficulty, we have some images that have been collected beforehand. But what we're going for, we're going to give you some water that has a little bit of moss in it. And it turns out this moss is often populated with little creatures called tardigrades. And you can't see them with your naked eye, but using our microscope, we will verify the research of Leeuwenhoek and discover that these organisms do exist and they're there. So the basic steps are to take your cell phone or tablet, and we'll be using the front camera, and we're going to put a little drop of water over the front camera, and this little drop of water is going to act as a lens, and that will be a spherical lens for our microscope. And then you all receive some Post-it notes. Hopefully you have those. If you don't, please ask if you don't have any of these things. And we'll be using these Post-it notes to hold a cover slide, and we'll put a little drop of water with the cover slide on there. And then we use that to get our slide in the right imaging plane, and then just snap a couple of images, save them to your phone, and later we'll be using those images. The next step is to be uploading the images to a data publishing service. So there's little YouTube videos you can click on here to get a better idea of what to do. So we'll go around, and hopefully you should have their materials. If you don't have anything, let us know. And we'll start with the data collection. And we should have a good 20 minutes to try this. Okay? So please ask any questions if you have any. we'll come around and help.
For doing this, so work with your partner because you're going to need one person to manage the cell phone and the other person to manage the project. And we're going to give you slide covers. Okay, so now because the purpose of this exercise is to go execute the entire arc of reproducible research. So what you're doing right now is data acquisition. You're repeating something that somebody has described already. And as you can tell, it's not always trivial to do it, and it takes multiple iterations. And that's what is so important, that the initial description, the initial instructions are very clear. And clearness only happens after you have done it multiple times. Now, once you have pictures in your cell phone, do whatever magic you normally do to get those pictures out of your cell phone into your laptop. So options are you could email the picture to yourself, you could tweet the picture as an attachment, or share it in Google+, send it to Facebook, whatever you normally do to share a picture, and then from that site, get it back into your hard drive. Once you have those images in your hard drive, we are going to use one of the common data sites or data sharing sites. The one that we're going to use today is called Figshare. And so Figshare started like the concept of, typically you see these articles that have diagrams and pictures, and the diagrams are usually squeezed into the text because usually you only get 8 to 10 pages in a paper. So the experience was that people were kind of frustrated with not having access to the real size original picture. So Figshare is kind of trying to fill that space or fill up that gap. So when you submit an article, you can put your figures in Figshare, the original images, the original picture, so people who are reading this article can go and find the original version. And what is really interesting about Figshare is that it gives you a unique identifier, a digital object identifier. So this is a URL that will survive, the destruction of the word in principle. And whenever you need to refer to your work, if you use this citation here, this URL that Figshare is going to assign to you, then you can have citations to your art, to your pictures or your data. Now, what does this matter? The idea is that if somebody else needs to replicate your work, they need to have access to the data. I need to know where it is. They need to know that they are getting the right piece of data. So when you put it in a place like Figshare and get a unique identifier, you can make this link and have the confidence that when you're describing that you analyze this particular image X, this has this unique identifier, and the person who's going to replicate your work know where to find this image. So you have already created an account in Figshare. It's a free account, so the usual drill, you just fill up your name and email, and you get an account. Now, because they are assigning you a real and digital object identifier, you want to have this to be very formal. So you're essentially getting the same unique identifier as a published paper will get in Science or Nature. So please, as you upload your images, make sure that you fill up the content of these fields in a serious manner. We ran these experiments 2 weeks ago in France, and the students were just putting goofy titles, and we got dinged for it. So, you have to show better. All right, so this is what we're going to do. Once you go to the Figshare site, your page will look something like this. And on the upper part of the screen, you will have the upload button or link. And then you can browse for files. You can just drag files into this from your desktop if you want, or click in the browse files and upload them. And go to your pictures files and get a recent screenshot, something like this. It will move up, and once you have it there, then you can go to sort files. So what is really important here is that we want the pictures to be public. So you're going to essentially publish the pictures by yourself. You will have a display like this one. And look at this column where you have the status column. Normally we'll have a button that says draft. You click on it, and then it's going to ask you a little bit of information about your image. So this is where you have to be serious and descriptive. So, mention that you're capturing images of tardigrades. Our friend tardigrades look like this. This is what you are receiving in the samples. These guys, have respect for these little guys. They can survive in free space. They can survive for 100 degrees. They can survive 1 year without water. So they are little, but have respect for them. So that's the title here. You put your authors. Normally it should be you and your collaborator. Put some categories. If you just want to use biology, we have like biology techniques. Biological techniques would be enough. put some tags that will allow people to identify your picture. Mention microscopy, mention tardigrades, and it is in description. Once you have done that, down here you have the public button. So once you click in that button and save your change, your image will be accessible publicly. So that will be the second part of the process. You have acquired an image with your image acquisition device. Now you're sharing that data. And data sharing is key because only with access to the original data, somebody will be able to replicate your work. Any questions? Yes?
The name of the creatures, how do you spell that?
Tardigrade. Let me put it here. Oh, not here. Yeah, that's the common name.
Those guys are in the SCP. Wow. I'm sure they have one here at the university somewhere.
So if you've uploaded your images to Figshare, there's also a notebook, a simple IPython notebook on data sharing. And if you look at that, that will allow you to, it teaches you how to use your data that was uploaded to Figshare or another network resource and download it locally in a cached way so that you can run your analysis. So that when you run your analysis script, you just use the short end of it is just one command. It's the URL lib. It's in the Python standard library, urllib.retrieve. And that kind of guides you through how to go through and take a lot of these data journals will have REST APIs, and it teaches you how to use the REST API, get a REST API, and find out how to get your data in your local Python script. So that's this guy right here.
Okay, so I'm going to talk about the computational environment really quick here. Hopefully, you guys are making good progress on setting up the system. And if you have any issues, let us know. We'll try to help you as much as possible. So really quickly, the computational environment is the requirement here because we're going to run our exercise on a system that can be consistent, or that will be consistent on different systems here. And what happens is that, often we have this question, like why this is important, why we need this consistent environment. And the reason is very, very simple. Because as things are changing, the libraries, the OS, the hardware, it's very hard to guarantee that you will have a consistent environment for your experiment, especially in the computing environment. So how do we do that? And that's what the exercise here is, like how we can create the environment which will work for the exercises that we have. So there are many ways you can create the reproducible environment. We actually are working on, for this particular tutorial, 2 of them, Docker and the VM. But again, it's not like that these are the only 2 options that you have. You can have more than these 2 options out there. So the Docker and VM, VM is for the virtual machines. From a 30,000 feet level, you can see that they both kind of gives you the same features, but there's a huge difference when it comes to the architecture of these 2 things are concerned. So think of Docker as the lightweight, isolated environment versus the VM, which is slightly more, heavy on the system. As you can see on this image, that the VM involves a host OS, well, a physical machine, a host OS, and the hypervisor. And on top of that, you have one or more guest OS or guest operating systems. So if you need like complete isolation, if you need more security, I guess, then the VM is probably the better choice. Although Docker is no less secure either, but it does have, by its architecture, it's actually it doesn't have that kind of separation. So you have the Docker engine that runs on your host OS. So what Docker uses is something called Linux containers, and because of that, it's traditionally it's much lighter weight than VMs. So hopefully by this time you all have the Docker or the Vagrant up and running. And one thing I didn't mention is that the Vagrant is a software. Again, it's not the only software, but it's one of the software through which you can create your reproducible environment. And there are multiple ways you can provision that. So the one that we have created for the tutorial is using Ansible, but there are many other options that you have. So again, there are multiple options. We just pick one that are most friendly, I guess, in a given time constraint. Now, one thing I should mention is the package managers. So part of the problem in creating a computational environment is the getting all the necessary libraries, because as you know that we have now complex softwares, and it's not very easy if I just give you instruction, hey, install Python, and Python needs 5 other libraries. So if there is no package management for Python, then that means that you have to install all those packages separately. You have to figure out like what versions they work together and things like that. So I hope that some of you or most of you know some of these things. So like on Mac, people use Mac ports or Homebrew. On Linux, depending on which variant you're in, you can use Yum, or if you're in Debian, you can use dpackage. So again, depending on which particular environment you're in, you will choose one or the other one. So with that, I believe we already have done this thing, but for the exercise, we want to create our own reproducible environment. And we have, actually, it says 3, but the third option is really the all by yourself. So it's really 2 options, out of which the Docker is the preferred one. Oh, I'm in the, okay. So I think at this point, most of you guys have Docker up and running. If you don't, let us know. But one thing, especially for the Mac users, because I see a lot of Mac laptops here, you are running the Docker container inside the VM. So it's a 3 levels. You have your host OS, you have VM, and the Docker. On Linux, that would be just 2 levels. So if it's confusing, let us know, because sometimes it's easy to miss that which console or which environment you are in. If you're on the VM, it should say Docker at something. So, and if you're on the actual container, there will be a different tag, so you can identify it through that. So with this, I guess we're just gonna see, and then if anyone needs any help at this point. Asking you on all those videos, especially on
We've just had a tip for some Mac users that double-clicking on the Boot to Docker app is better, potentially, than running the Boot to Docker app on the command line. So if you're having trouble on Mac, try that.
So hopefully things are working pretty well here. As the next step, we're going to just take 10 minutes. If you're having difficulties, you're not alone, but do your best here. And if the Docker didn't work for you or the Vagrant, you're welcome to just use your local installations of Scientific Python. But for the next stage here, we just have a little exercise in data processing. And this is just a simple exercise trying to go through the best practice of not duplicating your code and using reusable components. Just a general software development best practice, but you're saving yourself from many errors and helping your colleagues in running your code too, if we avoid copying directories and pasting stuff all over the place. So here, the IPython notebook, which I'm sure everybody's familiar with. We have a little exercise with a little IPython notebook that's set up for you with some basic data processing in the notebooks directory. And you can try that out on some of your own images. And at the end of the exercise, there's just an example of using modules that you create on your computer that if you're going to go, and later on we're going to go and reuse our code in creating our article with DEXY, and also in using it for testing. We want to have anything where we're using in multiple places, we want to have it in some reusable state. And there's different ways of doing that, but in this case, we'll put them into their own Python files, their own Python modules, and we'll incrementally get them in there. And there's an exercise on reusing a local module. And then also, if you have your images, or if you want to download one of the other images that were made available on the website and try those in the IPython notebook, you can try that and just play around with a little processing. So we'll do this for about 10 minutes, and then make sure to make some changes to this notebook, whatever it will be. And then next up, we'll have Steve from GitHub will come and talk about taking the changes that you made and managing them with revision control with Git and working with it on GitHub and making that software citable.
All right. I know some of you are still working on some stuff, but we're going to jump forward a little bit. My name is Steve. I don't do science, but I do work at GitHub. So we're happy to be sponsoring this particular event. It's really awesome to see the kind of stuff that you guys are putting up and using GitHub for, so we're pretty excited about that. Just wanted to talk to you a little bit about how we like to use Git and the workflow of Git at GitHub, and how it can work for you guys, and what kind of tooling we would give. But so the first thing that sorry, this is going to be weird. I usually like pace back and forth when I talk, and they told me I had to stay right here. It's going to be really hard. So we have we call the way we work GitHub flow. It just, I don't know why, but it tends to work for us. That process is, once you have a repository and you start doing some work on it, don't ever, like, we have a general rule, don't commit to master, ever. Just don't. Please don't. It's like, you know, with great power comes great responsibility. Like, it's easy to commit to master, just don't do it. It's like publishing without peer review, I promise. It's not good. So why wouldn't you commit to master? Because a lot of times it's just easier, right? It doesn't give any history or explanation as to why or what you're doing, and it assumes that you're going to be correct. And yes, you can revert stuff, but it's just better to work, especially when you're working with other people. But even if you're working by yourself, I still follow this workflow because it's nice, especially if other people are going to be joining in on the project later, or if I want to look back through and understand why I did things the way I did them. It's all much easier. So what we do is, the first thing you do when you're going to do some work is you create a branch, right? Branch from whatever your default branch is, normally the one you're working out of master or whatever that is. And you just create a new branch. Name whatever thing that you're going to be working on. Descriptive branch names are awesome. Sometimes people have protocols on how they name their branches. Sometimes it needs to start with a username or whatever. However you need to make that work, we're not very strict about it. You can do whatever you want. So the first thing is just creating a branch. Then you do your work. You add your commits as you normally would, do your tests, add your changes to whatever you're working on. And then, once those are committed and pushed up to GitHub, you open a pull request. How many people have actually opened a pull request ever? Awesome. I love you people. Pull requests are so great. They provide this marvelous mechanism of collaboration and chatter around the changes to a repository that not only provide you with some excellent mechanisms for discussion of the changes that you're going to be making, but also give you some history once those changes are actually merged or not merged as to why those decisions were made. So you can go back and look at a set of changes together and understand why those were made, what happened, who actually participated in the discussion, etc. Really handy. So that's the discuss and the review the code. Look at the changes, talk about the changes, figure out if it's what you want to do, if it's how you want to do it, talk about it, and then when you merge it, that beautiful little green button on GitHub just kind of sticks all those changes right back into master, and it just works. It's a really nice workflow for updating and changing your code. So I'm going to walk through a couple things on how it's easy to do that. So I've got the tutorial thing cloned, and this is my fork of the tutorial repo. And I am going to add, yeah, working on it. There we go. So I have this document that I wanted to actually add that is going to go over pretty much everything I wanted to talk to today. So I'm going to add that to the repo. I'm kind of go over how I would do that if I want to get this added in to the original repository, right? I'm on my fork, and I want to contribute to the one upstream. So how would I do that? First, I can see, okay, my untracked file, I have this version control document that I've added in. That's awesome. So I'll just, oh, wait a minute. Hold on, look at this. First off, I'm on master. So git checkout -b to create my branch. Yes? Yeah, let's see if I can make this window a little bit smaller too, so that it fits. Not a problem. Hey, all right. My prompt is like half of the thing. That's awesome. Maybe I can shrink it down just a tiny. How's that? That? Okay. So I'll check out. Now I'm on my version control document. This prompt is hilarious. So now I'm on my branch, and I can git status. Great. There's my doc. Git add dot or add-u is a common one that I do. You can add specific files. Add-u is a really nice shortcut if you have added and deleted files. That'll stage all your tracked files, including things that you may have deleted or not, all at once. It's kind of a nice little shortcut. So add that stages. Make sure of that. Yes, untracked files. Documents. I'll just add dot. There we go. So there we go, a new file. Git commit -m. I like to just do short messages right on the command line. Tip for commit messages, keep them short. Commit messages should be around 50 characters or less, ideally. If you really need to go into explanation, do that, but do that after you make a short opening line. It's much nicer to look through a Git log history if it can truncate to something short and meaningful. That is not just for GitHub. It's when you look at a Git log on your terminal. So keep your things short. Oftentimes, if I'm doing a one commit branch, it's close to the same as my branch name. So I'll add that. Git push origin. Boom. Sweet. So I push that up to GitHub now. And so if you look at my repository, you'll see one thing. Yeah. Can you see that? No? All right, it'll move around a little. So when you push something up on GitHub and you go to that repository, we kind of take note that like, hey, you pushed up some stuff that may be a branch you're interested in. So you'll see this. I just pushed this up. And I can compare and pull request. So what is this for? This starts my pull request document. And it lets me put in, I'll give it a title. I can add some description as to why I'm doing this, if it's a bigger change, or if it's something really I want to talk about. We oftentimes will open up pull requests long before the code is actually finished so that we can talk about it while we're working on it. So that's a big recommendation. Pull requests aren't just for when you think the work is done. If you want to talk about it with someone or present it before it's complete, it's a great place to do it, right here in a pull request. So I don't really have anything to add to this. So I'm going to create this pull request. So that looks like this. And then when I look at the pull request, so I didn't give a description because I didn't feel like typing. But you can see the commits that are in this particular branch changes, the files that have changed. You can see this. If you're doing markdown or text stuff, a lot of times it's really nice to see a rendered diff of this, so you can see the things that are added and how it works nicely. So then that pull request is submitted, which is interesting because now someone from, if I go over to the conversation, for instance, I have access to this repo, but a lot of times people who are contributing to a fork will not. So you'll notice when I did the pull request on the fork, it actually did the pull request onto the parent branch, not my fork, onto the upstream repository. So then if someone from, well, here, I'll just go ahead and do it. I'm just going to go ahead and merge it. Yes. Ideally, you don't merge your own stuff. Sometimes you can. It's fine. I'll delete that branch just to clean it up. Awesome. So now, here's what's really interesting. Now I should be able to go over and get check master, get pull. Wait a minute, it's up to date. What's wrong? Get log. My thing isn't in there. Why isn't it in there? Because I'm on my fork and it was merged into the upstream repository. So now I got to figure out how to get the stuff from upstream into mine. That's where this comes in. When you're working with a fork, the best thing you can do is add the upstream repository, so the thing you forked from, as a remote in the repo. You do that by, you can look at what remotes you have. So if you get remote-v, it'll tell you like, oh, I have origin, and that's where my origin repositories are going to. So I'm going to add one. I'm going to add the original repo, which is this thing right here. You'll notice now in the commits over here in the original one, there's my stuff that I did, but it's not over in mine yet. So git remote add, paste that URL in. Oops, I gotta name it. That's what I get for working too fast. Git remote add the name of the thing, then the URL. Upstream is what I'm gonna call this. Okay, then if I check my remotes, I'll see I have my upstream repositories there. So then two little lovely commands to get all the changes in. You can git fetch upstream. That just pulls down all the refs locally. You haven't done anything with them yet. They just exist now down here, and you can check them out if you really want to. But then I can git rebase upstream master. Boom. I like to rebase when I'm merging in upstream because it keeps the history cleaner. It doesn't create a merge commit so that that doesn't get pushed up if I do another pull request later in a different branch. So now you'll see git log has all of my new stuff in it, and there it is. You can actually do the same if you want to get this version control document and pull it down. Yes? Correct, yes. So git pull, if you git pull origin branch, whatever, master or whatever branch you're working on, that's going to pull down other people's stuff that they've pushed up. If you're not working on a fork, if you're just collaborating together on a repository that you all have access to. Yes.
Like I usually just like git pull and git pull.
Mm-hmm.
If I want to get the main one, I just use the git pull from the main.
That will work as well, yes. You can pull from the remote. So instead of git pull like origin master, you could do git pull upstream master. You need.
But this is the same.
Yes, it's essentially the same. Yes, it instead of pushing the commits on top, it actually rewinds your thing and then moves it all forward, so it keeps the history a little cleaner. It's the same thing. You'll end up with the same result. The git history might look a little different, but you'll end up with the same result. So And then if I want to actually have those changes up on GitHub, then I can just, now I can push all those changes up to my fork, and now my fork is actually up to date on GitHub with the upstream. So that's something a lot of people don't actually know how to do. I know a lot of people who, when they do pull requests, when they contribute with stuff, they'll actually like make their pull request, and then they'll delete their fork, and then they'll re-fork because they don't know how to do that step of like merging in upstream. So that's a little tip. Other than that, keep your branches small and tidy. Keep them focused. Avoid things like long-running branches when you're building stuff. Don't let a branch hang around for a month or two. Like, they should be small, compartmentalized bits. If it seems like something is taking a long time, figure out how to break it up into smaller bits that you can merge in. The other nice thing that we've done as well, you don't always have to pull request into master. There are times when if you do need to work on a long-running project, like if you're like, let's say you're rewriting a whole bunch and refactoring a whole bunch of your application, you can actually create a branch called refactoring and then create branches off of that refactoring branch and pull request into the refactoring branch over time. And then at the end of it, make a pull request for that refactoring branch that merges it all the way into master once it's all done. So that's a much better way of doing long-running things than just having things sit around for a long time. Any questions on that stuff? Yeah. Essentially, no. I think git pull -- rebase actually is this fundamentally the same as just doing git rebase, but I think it gives it in a pull in the command line reference the same as git pull does, because rebase is a little different.
Does git pull fetch the change from the server?
Yes. Yeah. Well, git pull will pull changes from the server again. Rebase, there are subtle differences between pull and rebase, and unless you are really, unless you really care about how your Git history looks, you don't need to really worry about them. That's if you're really interested in the underpinnings of how Git stores and tracks all of your data over time, which is very interesting, by the way, if you want to look into that stuff. But if you don't care about that, if you're too busy with your actual day job and the things you're trying to accomplish, don't worry about it. It's fine. Anything else? Cool. Thanks, guys.
So let's do a 10-minute break and come back in 10 minutes, get some coffee and good food.